Okay, so now let's write a Matlab script for Gauss elimination method. We have seen already how the Gauss elimination works, and in fact we have seen how to play with the arrays in Matlab. So first I will define my function. I already created a script named naive Gauss elimination. I will just give a same name. Then I will close all the windows. Then I will clear all the variables in the memory. So next is to define the coefficient matrix A. So let me remind you how we define it. First, I give the rows. So let's say that 13, 0.01, 5, or 4, doesn't matter. It is 100, 1, 21. This is my second row, and my third row is 6, 0, and 1000. Now for the right hand side of the equation, I will define, use capital B. Again, I will define a column vector. So it is 21, 0.001, so 1/10 to the power minus 4. By the way, I will put semicolon between them. And then I will write here 8. Okay, I don't want this to be shown in the screen. Now, first, I will begin with the forward elimination step. Okay, so let's see how the forward elimination is done. And let's go back to the slides. What I do in the forward elimination step is first I choose the pivot equation and pivot coefficient. Certainly the first equation is the possible choice for the beginning, and as a result the first coefficient of it is the pivot coefficient as logical. Then what we do is basically we first normalize the first equation with its coefficient, then multiply it with A21 and subtract it from the second equation. This is how we do. Also, we do the same thing for the right hand sides of the equation. Now let's return back to the Matlab. And in fact, this basically means that I have n minus 1 I need to make n minus 1 operations. So let's define the n here. I need to define the size of the matrix, number of equations, n. So this is for, I will use I1 for the row indexes. I1 is equal to from 1 to n minus 1. Okay. Then I have end. let me put a continue comment here. This is just for debugging purposes. Now I have the second loop for I2 is equal to I1 plus 1 to n. By the way, this has to be column, not a semicolon. Okay. And next is now I need to choose the pivot. In fact, I will do it here. Pivot is equal to I1 okay. Now here, first what we do is we normalize the first row or the pivot equation. Okay. Now when I put a semicolon here in place of the index, for example, the second index shows the column. When I put a column here, it gets the whole row. So let me show it to you like this. Just by debugging. I will put a breakpoint here and I will run it. You see, now it gets the first row because A1 is the one here, and it gets the whole first row because of this column sign. Okay, so n will not be here because I'm making an operation over the next set of rows than the pivot equation. Now what I do is first I divide it with the pivot. Then I multiply it with the next set of rows, which is I2 here, and the column number is the row number of the pivot element, pivot equation. So basically what I do here is, if this is my first element, I multiply the first column and second row with the normalized value of the first row. Now what I'm going to do is I will subtract it from the second row. And let's check whether it will work. I will put in another continue command here for debugging purposes again. Then I will put in another breakpoint here and I run it. You see, the second row is modified now. If I press continue once more, then it will do the operation on the third one. Now let's continue. Okay, so let's put A here for debugging purposes and let's see how it works. because we didn't assign anything. Okay. Yes. Now, as you see here, first column from the equations, now the variable x1 is eliminated except then the equation 1, as you see. Now if I press continue once more, now here you see that x2 is eliminated, x1 and x2 is now eliminated from the last equation. Now the forward elimination step is ended, but the point is we have to modify the right hand side of the equations as well. Now for this purpose, what I'm going to do is, instead of using a new variable, I will work on the right hand side of the equation b, because I don't want to allocate new memory. Sometimes you have to be memory efficient. So for this purpose, what I'm going to do is I will copy this line and put it here. Now remember that I'm working on the right hand side b. First I divide it with the pivot, then I multiply it with the coefficient of the second row, then I subtract it from the b2, then I will assign it to the bi2. Now let's see how it works. Again, I exit from the debug mode. Now I have my breakpoint on the line 17. So after the first row of iterations, these are my b values. I say continue. Now it's once more modified. Okay, so let me check it once more in order to be clear about it, be sure that it works. I eliminate it and I will run the debug mode once more. Okay, this is after the first set and this is after the second set. Okay, yeah. It appears to be working. It appears that it works. So I have A and B after the forward elimination. Now I can delete this line. I don't need it anymore. Now next thing is the backward elimination. So let's go back to the backward, how the backward step works. So this is my forward elimination. This is okay. Now I obtain this expression, upper triangular equation. Now the backward elimination will work. So I will begin from the last equation, from n, and then I will go to the next set of equations. Okay, here is my expression. So I have a backward loop iteration. Now let's return back to the Matlab screen. This is back substitution. Now for I1 is equal to n minus 1 to 1 with the step sizes minus 1. And so okay, so we go from n minus 1 to 1 with negative increments. Let's check whether it will work. Let's do some iteration. Yes, it goes from 2 to 1. That's okay. It appears to be working. So I will put the same column here. I don't need it anymore. But first thing is to find the value of xn. So xn is equal to b n divided by a nn I will put in another breakpoint here. Okay, so it gives me the complete x. So it is minus 0.0025. This is what it found. Now I will continue for the back substitution. So let's go back to the expression and see how it works. Okay, so I have a here a matrix vector multiplication beginning from the previous values I plus 1 to the last equation, and then you multiply it with the corresponding values for the xi, and then you divide it by the ai1. Okay, so let's see how we can do it in Matlab. First, I get the values I1 plus 1 to n. So these are the values. And I will put a continue line here. again for debugging purposes. Now here it is 2, it is 2 plus 1 is 3, 3 to 3. It should get the A11 value, whole set of columns. Just a moment, please. Sorry, I made a mistake. This has to be from, yes, this is I1 from I plus 1 to n. And now let me run the script. Yes, now we get the correct value. This has to be multiplied by the column vector x. This has to be I plus 1 to n. Now let's check the operation once more. Yes, now it's correctly found. Now I will subtract this value from the BI1. This is also okay. And now this will be divided by A I1 I1. And this will be the value for xi. This is the back substitution step. And let's see whether it will work. It appears to be working. It gives us an error. So what's the error? Error using multiplication. For multiplication, check the number of the columns in the first matrix. So both are understood as a vector. So let's check the variables again. Let me run it once more. A is 3 to 3, and these are the columns. This is 1 to 3. Let's assign it to the dummy variable in order to understand why it makes like this. And let's see the size of the dummy. This is 1 to 1. Okay. Yeah, it's 1 to 2. So this is why, therefore, I have to take the transpose of. I have to take the transpose of this matrix, this vector, sorry. Because xn is understood as a row vector, because I didn't define it beforehand. So now it should work. Let me set a breakpoint here. Okay, after the first iteration. Yes. Now I got the values. Now I can put semicolon to the end of the lines because I don't want to see the values. I don't need these lines anymore. I only need the x value. I don't need to continue lines anymore also. I don't need to evaluate them. So I need the final value of the x only. Let's run it. Okay. So let's validate the result. I say that A0 is equal to A because I'm modifying it. B0 is equal to B. Now x is equal to transpose x. So A multiplied by x minus B is my error. And let's see whether it works or not. It has to be small transpose. Huh? Yes, it is 0. So our elimination, naive Gauss elimination works. And so next thing is, let's improve it by the pivoting. Okay. And I will save it with a different file name. Gauss elimination with pivoting. P. Or let's say pivot. That's okay. Now I will use the same routine for it. And the point is this. I will use the same matrix. So what was partial pivoting? Basically what I do is I choose the largest of the column in the forthcoming ones, because you know I can easily but pivoting here I will do a partial pivoting, not full pivoting. In fact, in full pivoting you both look at the column and row. Okay, so in fact I will do partial pivoting. I'm going to look at the maximum and in the forthcoming columns, forthcoming rows. So let's do it like this. I will begin from the first one and I call the first row of elements. So I'm just looking at the first column first, sorry. And I will get the max value of it. As far as I remember, the command was maxval, but I will check it. I will look for the help on it. Yes. No. Then it is max. Okay, that's nice. Now max A will give me the maximum value, and if I write it like this with I, it will give me the index also. Let me try. So I say max value and index, and I put it in square brackets. So I'm just looking at the first column at the moment. And I put a breakpoint here. A max value in the first row is 100 and its index is 2. So I have to change the first row with the second row. I have to change the places. Now for this purpose I generate a vector let's say dummy vector one, and that is equal to A I1, and I get all the values in the A1. Then I will have the dummy vector two, and instead of using I1, now I use index. This is okay. So I copy this line Okay, so this is equal to A I1, okay, and A I1 is equal to dummy vector 2. So I get the whole vector. And let's see whether it will work or not. I will put two A's here for debugging purposes again. So these are my matrices. Maximum value is 100, maximum index is 2, that's okay. And this is my original matrix. So let's put a semicolon here and let's run it once more. Okay. So I changed the row 2 with the row 1. As you see, these two rows are the places of the rows are changed. Certainly the Matlab multiplies these values with 10 to the power 3. Okay, so I don't need these A's. It appears to be it's okay now, and in fact I don't need the dummy vector 1 now. But one thing is, I have to change the places of the B, the right hand side vector. So let's say that I have a dummy variable now. And this has to be equal to B index. Because I have to change the places of the B's also. So B index is equal to B I1 and B I1 is equal to dummy variable. Now B1 is already defined, B index is defined, so the right hand side is also already changed. Now the pivoting is completed. So basically what I do is, instead of changing the whole rows, I change the places of the equations in each step and check it. Now let's see whether it will work or not. I put the breakpoint here. I exit from the debug mode. Now my pivot is 100. That's correct. So I don't need to change anything else then, of course. And furthermore, B has changed also, as you see, the places of the B. So the second row and third row is already changed. Now I will continue. Now my pivot is 1. In the second row, it's the maximum value. Okay. I have some negative values, but perhaps I might look at the absolute value of the pivot, but in this case, it's not a problem. So first and second row is, well, I have to look for the rest of the equation. So now I find another mistake. Because I'm looking at the complete row. But I should look at from I1 to N. Okay. Now it's okay. I run it. Now let's look at the B value. Now as you see, the first and second row is again has changed. Now I will run it once more. Now second and third is changed. And I end up with the result. I clear this breakpoint and I have the X values. 175 minus 175 and minus 0025 for the X3. And this is with pivoting. Now the scaling is, remember that you divide the whole expression with the maximum of the row. I will continue from the same equation. Now there are different approaches. You can dynamically scale the equation at each step, or you can scale everything at the beginning. So this is two different things. You may follow different approaches. It's just an experience, but sometimes scaling is also good So basically what you do in scaling is you divide the whole expression with some value, you normalize it, and all the values becomes at an order of 1. So here I will put a explanation for here. It's pivoting. That's also okay. In fact, I don't need these lines anymore. And let's make an explanation here. End of pivoting, partial pivoting. Because in full pivoting you also look not only the column wise but also the row wise. This is the partial pivoting part. It may be better for you if you give some spaces for different parts of the operations in order to debug the code. Now scaling. End of scaling. What I'm going to do is for scaling is maybe it's better if you do the scaling before the pivoting. Here, okay. So basically now I will get the max of each row and divide the whole expression to the maximum value in each iteration. Of course, this increases the CPU time, but sometimes it improves the numerical accuracy. So I will put in another line here for I1 is equal to 1 to n. Sorry, this is I2, huh? Now I will look for the row wise. And I say that it's max value. So this is what the maximum value of the A is. I get the maximum value of the A. And I assign it to the a variable. Now I1 is equal to, I'm looking at the row wise A I1 divided by maximum value. I will put a continue line here. I put a breakpoint here. Now I will just run it. You see that my first equation is normalized with the maximum value. Now this is just how it is shown on the screen, but it is 1 and the other values have some finite value. I will continue for the second line. That's also okay. And I will do it for the third line as well. Sorry, this is not A1. This has to be A2. Okay. Let's get out of the debugging mode again. Yeah. Now first line is normalized. Second one is normalized. And the third line is normalized. Now I have to apply these steps to the right hand side also. Okay, first line is normalized and the second one is also done. Yes. And finally the last one. Yeah. So all are normalized. Now all the equations are scaled, and it will be scaled in each at each step. So let's check. Oh, we have a problem. I made a mistake somewhere. It appears to be correct. Now here is the point. Because of the negative values, we have to consider the absolute value of the maximum. And the code finds 0 as a maximum. Okay, now it should be okay. Also here we have to use absolute value. Sorry. This absolute has to be inside. Okay. Yeah. And we have to use the absolute pivoting also in order to avoid division by 0. Now let's check. Let's get the help for absolute. It seems okay. I forget a comment here. So what's the problem? Okay, so it appears to be that we made a mistake in the index. So let me show it to you. Now we did the scaling, but in the first part of the pivoting, luckily it works pretty fine because of the numbers. And the point is, now we have the index here, right? And we get the index of from I1 to the N. And index is just, for example, from 1 to N, so 1 to 3, it is one of the 3. But when it is 2, it is 2 to 3, and it's a vector with a 2 elements, and the index value can change from 1 to 2. As a result, we have to add a value to here. So I1 plus, or we have to modify the index, that's better maybe. I will modify the index here. So index here is index plus I1 minus 1. So first I will comment this and show why it happens like this. Now for the first iteration it's okay. I will exit from the debugging mode. Okay, so this is my value. Remember that I1 is 1, okay, N is 3, and I'm looking for the 1 to 3. So the maximum value of the first column now. And I will choose 1. It will either give me 1 or 2. It will give me the 1 automatically. So it gives me the 1, the first one. That's okay, no problem about that. Anyway, is okay for us. But I will continue for the second one. Now let's look at the matrix A. As you see, the first variable is eliminated from the matrix. Now I will look at the second row, and the value is 0.0945 and 0, 0. So A is a 2 by 2 matrix, and in fact it should give me 2 in this case. The index has to be 2, and let's see what it gives. It gives me 1. And I1 is 2. So basically I have to modify it. I have to modify the index value properly. So index has to be index plus I1 minus 1. Now it should be okay with the scaling. Let's see whether it is or not. Let's check the A. Yes, it is upper triangular. So it seems to be okay. And I will continue. Yes, now I have the correct values for the matrix. Okay. Now my scaling is already done. And now there is another thing. Remember that we talk about the or we talk about the ill conditioning. So there is something called condition number. So we will look at the condition number and how we can calculate the condition number now. So now the condition, in order to calculate the condition number, I don't know whether there exists a function for the condition number. We need to calculate the eigenvalues. It is better if we do it here. And let's check whether there exists a function for it. Or let's look at from the Google. I'm not using. Let's see how we can calculate the eigenvalues in. So this is condition number, but I will write here in Google eigenvalues in Matlab, and it gives me this help. So the command is 8. Simple. That's good. Now let's return back to our Matlab screen. So it's not, let's say, lambda for it. And this will give me the eigenvalues, and let's see the eigenvalues. Here are the eigenvalues of this 3 by 3 matrix. Now I will calculate the absolute value of it. And the second thing is the condition number. I will calculate the condition number. So it is maximum of the eigenvalues, absolute value of the eigenvalues, lambda, divided by the minimum. Now we have the condition number for this matrix. Okay, let me put a breakpoint here, quit debugging mode, and let's run it. Okay, now here is something critical for us. You see that we have a value 1 10 to the power 3. What it means, remember that we have round of errors, and round of errors can accumulate, and it is due to the number of operations. Okay, and remember that in the graphical methods we show some graphs of two-dimensional or set of linear equations with two unknowns, and in some cases you see that they represent the lines which have very close slopes. This is what we call ill conditioning. Now the point is this: when the condition number of a matrix, so basically the condition number is defined as the maximum of the absolute value of the eigenvalues to the ratio of the maximum value of the maximum absolute value of the eigenvalues to the minimum absolute value of the eigenvalues. This is called condition number. And here, as you see, it is 1 10 to the power 3. What it means, remember that we talk about the number of bits and its effect on the precision. This basically means that 10 to the power 3 means that you already lose 3 digits from the accuracy just because of the conditioning of the matrix. So because of the slopes. This is what the condition number means for us. If the condition number of a matrix is very large, this basically means that your matrix is ill-conditioned, and you have to use special techniques in order to solve such set of linear equations. We call those techniques preconditioning techniques. It's out of our scope at the moment, but the point is it will help us in evaluating the accuracy of our solution. So it's good to calculate it, and luckily calculating an eigenvalue is not an easy task, but Matlab does it for us. So that's something that you can check. Okay, so this is the condition number that we have. Now next thing is, we have already wrote our Gauss elimination script, and we obtained the unknown vectors or unknown values x. Now the point is this: I want to generate a larger matrix. Let me generate an arbitrary matrix with n is equal to 100. And let's apply the Gauss elimination. Now I know that my script is working. So for this purpose, I can use for I1 equal to 1 to n, for J1, now I will do it 1 to n. That's okay. So I1 J1 is equal to sine I1 multiplied by J1 divided by N square multiplied by P. Let me check whether it's capital P or small p, I don't remember. Okay, it is defined in Matlab. So I create a matrix. Now I will create the right hand side. EI1 is equal to cosine I1 or let's divide it by 5 maybe, yeah. I'm just generating an arbitrary matrix in the meantime. So it is divided by N divided by 10 and I will divide it by P. I will multiply it with P. So I will just generate something and now I want to plot my matrix. I will use contour command for it. I don't need to define any coordinates at the moment. I want to just see the outcome. So this is let me share it with you. Probably you don't see it. Yes. Now this is my outcome for the contour. You see, this is my index 1 here. So horizontal and vertical components are my indexes, and this is how the values are changing. Now let me do it in a nicer way. So I will return back to my Matlab screen again, and I will check whether there exists another, or let's go to the Google. Now, okay, I have a contour field command. So I will use this one in order to visualize my matrix. Again, I will put a breakpoint here. Now the field contours. Okay, let me share it with you. So this is my matrix now, and you see how the values are changing in the matrix. Okay, so from 1 to 100, you see that it is wavy. So the values are wavy. So I don't need numbers. For example, here 10 to 22 is 0.98, and here it is minus 0.99, and so on. Let's go back to the Matlab, and let's check the condition number of it. Oh, it's very bad. Condition number is very high. Okay. But we know that our elimination algorithm is working. So it is 10 to the power 17, the condition numbers. Fine. So next thing is the CPU time. For that purpose, I will again okay, so next step is the CPU time. So there is a command CPU time. So we will continue with the start time. It is CPU time. This will initiate give us the CPU time when we run this command, and then I will put end time here. That is the CPU time when I call it. So time for forward elimination is equal to end time minus start time. Now I will call again start time. Now I will calculate the CPU time. I will just copy these two lines and then copy and paste. I don't want to write them again. Okay, it's here. So it is end time, and this is time for back substitution. Okay. Now I will put a break. No, I will not. I will just directly write it. Time for forward elimination and time for back substitution. So this will give us the CPU time for these operations. So let me run it. It gives an error in line 63, so let's check it. why it gives me an error. I will run it once more. Okay. Now, for the forward elimination, the time spent is 0.2 seconds, and for the back substitution, it is 0.06 seconds. And from here, I can easily calculate the total time spent for the Gauss elimination part. You can play with it. So just watch the video. I know it's a little bit lengthy, but probably I forgot something somewhere. Ah, it's here. Yes. Okay. So this is why I see those numbers flowing.